So in this video, I will teach you about entropy and the third law of thermodynamics. So in our previous video, which I'll link to somewhere above and in the description beneath this video, we talked about change in entropy, or delta S. Now, although change in entropy can be either positive or negative depending on the reaction process, the individual entropy value, S, that's S without the little triangle in front of it, of any compound, molecule, or element is always positive, or at the very lowest, it can be equal to 0. But the value of S is only 0 at absolute 0, which is 0 kelvins, equal to negative 273.15 degrees Celsius. We see then that any individual S value is never negative. This fact is summarized beautifully by the third law of thermodynamics, which states that the entropy of a pure crystalline substance at absolute 0, which once again is 0 kelvins or negative 273.15 degrees Celsius, is 0. With that said, we now move on to standard molar entropy values. So as we learned back in chapter 5, that I'll link to somewhere above and in the description below, we can measure delta H, which is the change in enthalpy, by using a technique called calorimetry. Unfortunately, there is no similar or comparable way of measuring delta S, change in entropy. However, because the third law of thermodynamics that I just mentioned establishes a 0 point for crystalline substances, that is at 0 kelvins, we can extrapolate individual entropy or S values from there. Before getting into that though, I want to bring you to a standard molar enthalpy values example problem, which is a review from chapter 5. By definition, at room temperature, 298 Kelvin, the value of delta H of formation at standard conditions equals 0 for which of the following? Now, I'm not going to answer that for you here, but I will post a link here to a separate video that you can click if you want to go and see the answer. Let's now return to standard molar entropy values. So the figure shown right here displays how S values for individual substances change as temperature is increased from absolute 0. Please pause the video and take a moment to look at this. Here's a quick question. Why in the world does S, or entropy, go up so dramatically at melting and boiling points? All right, here's my explanation. I like to think about substances at a molecular level as being like this. Solids, individual molecules or atoms, move like this. Not a lot of disorder. They're very organized. By comparison, liquids kind of do this, and gases are like this. As you can see, solids are much more organized, very low entropy. Liquids are kind of in the middle, and gases are very disorganized, high entropy. Got it? You can see then that as you raise temperature of a solid, its molecules or atoms individually start moving faster and faster with increasing temperature. Therefore, they have more disorder, increased entropy. Eventually, however, they start to melt. As they melt, they go from being solids to being liquids, much more disorganized. Thus, the individual entropy values, or S values, for the substance go up considerably. The analogous thing happens as liquids are boiled or evaporated or vaporized off into gases. They go from a liquid state to a gas state. Really high entropy, which hopefully explains why we see such a dramatic increase as we go from one state to the next with raising temperatures. With that background in place, we can hopefully answer the following sample question. As water slowly cools from gaseous temperature to freezing, what happens to its entropy? I invite you to attempt this on your own, and if you like, you can click the link floating over here or in the description below to jump to my answer video. Returning then to standard molar entropy values, entropy plots like the one that I just showed a moment ago can be made by carefully measuring how the heat capacity, which we discussed back in chapter 5, linked to in the description below, of a substance changes with temperature. According to our book, the theory and methods used for these measurements and calculations are beyond the scope of this text, which I personally really believe and therefore will not explain here. Nevertheless, we can obtain individual entropy values, also called standard molar enthalpies, or S0, of different substances at different temperatures. Several of these are shown at 298 Kelvin, which is 25 degrees Celsius, around room temperature, in table 19.1 posted on the next slide, as well as in our book. Even more of these can be found by looking at Appendix C on these pages in our text. Here then is that table, which you're welcome to pause and look at for a moment. Now, in order to understand this more fully, we have to address some more S-ing details. There are a number of details then that we need to point out regarding a substance's standard molar entropy, or S0. First, you might remember from Chapter 5, again linked to somewhere floating above me or down in the description below, that any pure element's enthalpy of formation, delta HF sub naught, is equal to 0 if it's in its correct physical and chemical state. Now, this is not true of standard molar entropies. It should follow from our earlier explanation that standard molar entropies of gases are greater than those of solids, because gases are way more disorganized, hence more positive standard molar entropy. Third, standard molar entropies generally increase with increasing molar or atomic weight. And last, standard molar entropies also generally increase with an increasing number of atoms in a substance's formula. More atoms means more movement, means more disorder. That hopefully lays the groundwork for this problem, which I discussed in an earlier video, and whose answer you can see in the link that's floating over my head or somewhere in the description below. Let's now move on. How in the world do we calculate the change in enthalpy in our standard condition for reactions? Well, by looking up individual substances' standard entropy values, or S0s, we can calculate the delta S0 for any chemical reaction by using the equation shown here, where this term for products represents the sum of all of the individual S0 values for the products, each one being multiplied by its individual coefficient, and this term for reactants represents the same, just for reactants. And as you might surmise, guess what? You can do the same thing for enthalpy values too. That brings us to a beautiful question. Using standard S values from Appendix C in our text, what is the delta S value for the following reactions? I invite you to attempt this on your own, then you can click the link in the description below to access a different video where I'll show you how to work it. And this one, basically the same question, asking us what the delta S0 is for the reaction shown here, given the values shown in this table. And another one, using the data from Appendix C in our text, what are the values of delta H0 and delta S0 at 298K for the reaction shown here? As before, I'll put some links in the description below or floating over my head, depending on what YouTube allows me to do, that you can click in order to see the answers to these questions. That ends this video. Thank you so much for watching. In the next video, I'll talk more about enthalpy and Gibbs free energy. Until then, please have a wonderful rest of your day.